Hello everyone. So in our previous video, we have discussed the design of singly reinforced beams. And we also have discussed about the typical steps in us designing our SRB. And one of the most important steps in the design of SRB is the determination of the required number of rebars and their respective diameters. Okay, so in step number 5, we have discussed these methods here, which you can use. So you can use method 1, 2, or 3. So it will be up to the designer which one of this he or she will be using. Okay, so again, in this method, you can now solve for the required steel ratio. And from that, you can now solve for the required steel area. Okay, so once that you have already solved for raw required or AS required, take note that according to the code, we have our limits. So the first limit is the minimum. So the code states that the actual steel ratio must be greater than or equal to the minimum steel ratio, and it must be less than or equal to our maximum steel ratio. Okay, so if we would be converting this into area, so if we would be multiplying it by our base and by the effective depth, we can also say that the minimum steel area must be less than or equal to the actual steel area, actual. And from that, it must be less than or equal to the AS max. Okay. So, in a situation wherein the required area is, let's say, less than the minimum steel area, it means that you will now be rounding them up and you would instead make use of AS min as your AS actual. So again, in this situation, your AS actual is now equal to AS minimum. Okay? And in a situation wherein, let's say that your AS required is now greater than AS min, and it is now less than AS max. Meaning that for your AS actual or your steel ratio to be used is now equal to the AS required. So meaning guys that if it is within the limits, then you will now be making use of your AS required. But what if for a situation wherein, suppose that your AS required, so the AS that you have solved for, is now greater than AS max. Okay, so unlike in this situation here, whereas you had just made use of AS min, you cannot make use of AS max. Okay, so if your AS required is now greater than your AS max, I should say, what you would be doing, so you can do a couple of things. So you can either assume for a new trial section. So again, method 1 is increase your size. So increase section size. So that is the first thing that you can do, if you can. But suppose that you have a certain problem wherein the size will be limited. So in this case, the beam is limited to a breadth of 350 and an effective depth of 420. So in those cases wherein you cannot increase the section size, so another thing that you can do is by using, so use doubly reinforced beams. Okay, again, if let's say the total area required is now greater than AS max, either you increase your section size, or if you cannot increase your section size, just make use of doubly reinforced beams. Okay, so going back here, for rho max, equation number 2 here, whereas rho max is equal to 0.85 F prime C over Fy times beta 1 times 3 over 7. Again, this is in accordance to NSCP 2015. And as a review from our previous video lecture, that this is in reference with a strain of steel equal to 0.004. And for rho max here, so for rho max here at the bottom, if you want to ensure that your reinforced concrete beam will undergo tension control, so this is in reference with strain T equal to 0.005. Okay, so going to this graph which we have been seeing for a couple of times now. So according to NSCP, suppose that this red line here is our limit for a strain of 0.004. So let me just redraw that. So suppose that this is the line, for example, for 0.004. According to our code, we can only design our beams in this region only. And from that, guys, we cannot make use of this area. Okay, once again, when we are designing concrete beams, or yes, concrete beams, we can only make use of this region here. Okay, so as a review, what is a compression controlled or a tension controlled section? Suppose that we have a certain beam here. So let's say that this is now our beam. We can say that it is tension controlled if the one failing is at the bottom part, or at the not entirely the bottom part but the tension side. Okay, so if the tension side will be failing, that is now what you would be calling tension controlled. And we actually like this manner of failure since it is a ductile manner of failure. So ductile failure. Okay, so for compression controlled, suppose that we have once again a beam here. And for compression controlled, what that means is that the compression side is the one failing. So meaning, suppose that this is now our tension side. The failure will now happen here at the compression side. And if the failure is on the compression side, meaning that it is not really a ductile failure, rather it is a brittle failure, which is more abrupt, and with that, guys, it is more dangerous. Okay, so again, that is the comparison between tension controlled and compression controlled. Okay, so according to the code, we do not want compression controlled failures in our design, so we are not allowed to design anything there. Okay, so suppose that we already have this beam. How can we ensure that the failure will happen on the tension side? So in order for us to ensure that the failure will now be on the tension side, suppose that we have already underwent or went beyond the limit of AS max. So again, guys, going back here, if let's say, guys, your rho required is now greater than this rho max here, it means that the section that you are designing is already in this region. Okay, so it is already in this region. But if, for example, that the rho required is less than, so in a situation where as your rho required is less than your rho max, it means that in your design, it is in this region here, which is allowable. Okay, so once again, what we want to happen here is for the tension side to yield or to fail, not the compression side. So in order for us to do that, guys, we must, of course, reinforce our compression area. So let us just make it stronger by adding steel reinforcements there. So upon adding our steel reinforcement, of course, by common sense, our compression area will now be stronger. And if it will now become stronger, then there is a higher tendency that the tension steel would now be failing and not the compression side. Thus, from that, guys, we now have our doubly reinforced beams. Since we have our reinforcement at the tension, and we also have our reinforcement at the compression side. Okay, recap. So if you can design your concrete beam using SRB only, then just design it using SRB only. But in a situation wherein suppose that you have designed your SRB in such a way that the rho required or the AS required is greater than the maximum AS, then it is either you will be changing your trial section, or if you do not want to change your trial section, that is the time whereas you would now be designing it using DRB. Okay? So, our approach here is that, of course, the strength of this member here is now our VMN. And for the value of mn, guys, so for the value of mn, I will now be dividing it into two parts. So suppose that this is now the total nominal moment or nominal strength of our concrete section. I will be dividing this into two nominal moments or nominal strengths. Namely, this is now mn1 and this is also mn2. Okay? So if you would just be adding them, so mn is now equal to mn1 plus mn2. But what is mn1 in the first place? As you can see here, this is just a singly reinforced beam, and our basis here is our from Romax. Okay? So our basis here is now our Romax. And for the mn2, our basis here is whichever is left. Okay? So in that situation, so since mn is equal to mn1 plus mn2, we can now say that mu must of course be less than or equal to pmn. But in our situation, we can just equate them. Mu is now equal to phi mn. And since our mn is now split into two parts, namely mn1 and mn2, we can now write this as mu is now equal to phi times mn1 plus mn2. Okay. So from this equation, guys, of course, you know the value of mu. So since you already know the value of mu, you do not know the value of mn1 and then mn2. For mn1, you can actually solve for the nominal capacity of your SRB. So you can now solve for that. And now for mn2, once that you already know the value of mu and mn1, you can now solve for the value of mn2. Then from that, you can now design or you can now solve for the total AS prime required and AS2. Just take note, guys, that for the, okay, so for the compression bars, so that is now equal to AS prime. But for the tension bars, that is now equal to, you would just be adding this. So basically, AS is now equal to AS1 plus AS2. So from that, tension bars, I should say, that is now equal to AS. And take note that AS is equal to AS1 plus AS2. Okay, so we will be having a sample problem in the next video. And before anything else, if let's say that we have this particular section and I will be drawing its strain diagram. So for the strain diagram, suppose that this is now our strain diagram here. If this is our strain diagram, take note that the allowable or the ultimate strain of concrete, strain U or strain C, if you will, that is now equal to 0.003. Okay? And as for the strain of steel here, that is of course strain S or the strain of steel. And since we now have a new entity here, which is AS prime, we now have once again another entity here called strain S prime. Okay, so how can we solve for strain S prime? So looking at this strain diagram, and once again, this value here, this compression side here is of course equal to C. Okay, so this is equal to C. And from those, looking at this triangle here, so what I would be doing is that I will be comparing this small triangle here. So once again, I will be comparing this small triangle here by the bigger triangle here by ratio and proportion. So from that, guys, so also this is now what you would be calling D prime. So this is now a new entity called D prime, or the distance from the compression fiber up until the centroid of your compression bar. So that is now D prime. So again, I will now be getting the ratio of this triangle first, the smaller one. So that is now equal to strain S prime. So that is now strain S prime, this strain S prime, divided by this depth here, which is C minus D prime. So this is now equal to, so I will now be comparing that with this bigger triangle here. So that is now equal to strain U divided by, so strain U and its partner is the value of C. Okay, so from that, cross multiplying, this is now equal to strain U times C minus D prime divided by C. And substituting known values, strain S prime is now equal to, so for strain U, that is now equal to 0.003. Then for this one, that is still C minus D prime divided by C. Okay, so that is now our strain S prime. And as a review, that for the value of stress, that must be equal to strain S prime times E of 200,000. So by multiplying this by 200,000, so from that, guys, Fs prime is now equal to 200,000 times 0.003 times C minus D prime divided by C. And from that, guys, our Fs prime is now equal to 600 times C minus D prime over C. Okay, so this is a new equation that you should memorize. So it is actually easy to memorize once that you already know the value of Fs. So Fs is actually equal to 600 times D minus C over C. So just change this D minus C over C into C minus D prime over C. Okay, so with that, guys, we will now proceed to our design problem.